there's a reaction that's first order, and the rate constant is 0.39 per second at 600 Kelvin. What is the concentration after 0.29 minutes if the initial concentration is 0.37? So this is a, so this one here is a integrated rate law question, okay? It's a first order one, and the equation will be given to you on a periodic table. You just need to know where it's at. Obviously, to do this, you will be seeing it on a practice test, okay? So ln AT equals to minus KT plus ln A naught. Now, the trick here is you have to notice this here is seconds, this here is in minutes. I'm going to go ahead and convert this to minutes by just from minutes to seconds, just times 60, okay? And then your K here is given, we put that here, and then the time will go here. So that both will be in matching time units. Both will be in seconds. And then ln A naught, the A naught original is 0.37. You're looking for this AT here. Okay, so we just plug it all in. So minus K is 0.39 per second. T will be 0.29 times 60. That will give me seconds too. And then plus ln 0.37. Okay, so that is going to add up to be negative 7.78 altogether. And then that equals to ln A to the power T. Take E on both sides. Okay, and you will get it's 4.17, but it does 4.17 times 10 to the minus 4. All these questions all have just two sig figs here, so it's going to be 4.2 10 to the minus 4. And this will be molarity, and this is the concentration of AT. So in a question like this, it says, place your answer in standard notation 5 decimal place. That means you'll have to do 0.00, because it's times 4 and 4, 2. So that will be 5 decimal places, okay? Yeah, it's going to be a mix because most of them are multiple choices. It's going to be just like your regular test. You know how your regular test, off and on, you have something that's math that's open-ended like this, okay? It's going to be similar. But it's majority multiple choice. Maybe like 5 of them or maybe less are going to be math like this. But either way, you still get the answers, okay? All right, so this one here, the lowest delta G formation. Let's see who's the lowest. So in this case here, all these gases here are going to have 0 for delta G formation because they're the most stable form of that pure element at standard conditions. So all of these, since they're all zeros, they're all actually the same. The answer is all the elements have standard states that have a value of 0. Okay, so that would be our answer there. And let's take a look at this question here. So this question here, it says 25 mils of 0.150 molarity hypochlorous acid. Now, if you don't know what hypochlorous acid is, the formula doesn't matter, just call it HA, okay? And it's titrated with 0.150 molarity sodium hydroxide. What is the pH at equivalence point? So this pH equivalence point here is a weak acid because this gave you the Ka, and a strong base. I mentioned it earlier, there are going to be 35 questions in the final exam, and you will also see this stated on the practice exam. It'll tell you how many is on there. Okay, all right, so 0.150 molarity hypochlorous acid, 25 mils. So that should give you a weak acid amount, and then you're going to put a strong base in. So how much strong base would you need to titrate with this guy? So hypochlorous acid is going to be HClO plus NaOH. And then what you end up making is NaClO plus H2O. Okay, so basically you're just making the salt of it. Now, at equivalence point, you will have equal amounts of acid and base. You guys remember that? And because this is strong base here, your pH will be higher than 7. So you just gotta look for an answer that's gonna be higher than 7 there. So if you look at your answer choices, anything that's less than 7 will not be your answer, okay? So over here, you need to find out how many moles of acid is being put in so you know exactly how many moles of base has to be put in. Okay, so I can see that the molarity, both of them is the same here. So if I get 25 mils of hypochlorous acid, I know I'm going to need 25 mils of sodium hydroxide here because it's going to be 1-to-1 ratio. Okay, and then from the volume and molarity, I can actually calculate my moles. So you take 25 mils and then you divide by 1,000 because you want to turn into liters first, and then you multiply with the molarity, 0.150 moles per 1 liter. That should give you the moles of the acid, and then because it's 1-to-1 here, you know it's the moles of the base as well. Okay, so that answer here for our moles is going to come up to 3.75 times 10 to the minus 3 moles. Okay. All right, so 10 to the minus 3 moles. So we know you're going to use 3.75 times 10 to the minus 3 moles. And then you're going to react with 3.75 times 10 to the minus 3 moles, right? And then you're going to get 3.75 times 10 to the minus 3 moles of this salt, and then you have water. So the point is, when you have equal amounts in H and OH here like this, you are going to end up making a salt. And this salt, the reason is the pH is not at 7 is because this salt here is going to be slightly basic. Okay? Why do I know it's slightly basic? Because this anion here came from a weak acid, so it's going to be slightly basic. So the key is to know this. If you wanted to calculate the pH, you actually have to calculate it for this guy, this base ion here. So you write an equation for base here. So the ion plus the water, and then you base is the proton acceptor, you make HClO plus OH. Okay, we don't put water because it's liquid. And then everything else goes on our ice table there. So this will be like a weak base problem now. And then we have to find the pH. So then we need the molarity because you need molarity on your ice table, correct? Well, the good thing is I know how many moles I have. And I know what the total volume is. It's 25 and 25 added together. So I actually have 50 mils. So I'm going to look for the molarity here. I'm going to write it over here. Molarity is going to be 3.75 times 10 to the minus 5 moles. And then it's 50 liters, 50 milliliters, so 0.050 liters. Okay, so that's my molarity, and it's going to give me an answer of 0.075 molarity. So that value goes over here as my initial 0.075. Okay. And then this initially is 0 and 0 because water is not in there. And my change is going to be minus x, and plus x. Okay, so this will be 0.075 minus x, and then x and x. And then we're going to go ahead and cross this one out. We're going to approximate it because this is going to be small. Well, before we start, they only gave us the Ka, and you actually need, because this is a base equation, you need the Kb of this guy. So how do you get the Kb? Kb is going to be Kw, which is 1.0 times 10 to the minus 14, divided by Ka, which is 2.9 times 10 to the minus 8. Okay, so that's going to give me the Kb to work with, and it ends up being 3.45 times 10 to the minus 7. And really it's just around 3.5, but on my calculator it was a longer list of number. I just don't round, I just keep all the numbers on there and then write it. So let's set it up over here. So I'm going to go ahead and do the Kb is 3.45 times 10 to the minus 7. That equals to x times x over 0.075 minus x, which this one I'm going to go ahead and cross off. Okay, so x squared would be 0.075 times 3.45 10 to the minus 7. Okay, and that gives me the answer of 2.59 times 10 to the minus 8. To get just x, you square root both sides. So x will be 1.6 times 10 to the minus 4. And because this is a weak acid and the K here is really, really small compared to this number here, I'm going to go ahead and skip the check step here. But if you remember, if you wanted to check, remember you just take this x here, and then you divide it by 0.075, and then you can see it's less than 5%, okay? So do this here, you take your x. Now this x here is equals to HClO and OH. So from my x, I can actually get POH. Okay, so let's go ahead and calculate POH. POH is going to be minus log 1.6 times 10 to the minus 4. Okay, and then that will give me an answer of 3.79. Therefore, pH is 14 minus 3.79. So it will be 10.21. And then you just find an answer that matches that. Okay? All right. Let me know if you guys have questions. Other than that, we're going to keep going because we do have a lot of questions to cover today. And if you end up not having enough time, you have to go. This will be recorded and you can watch it later, of course. So it says here, which of the following processes show a decrease in entropy of the system? So that means you want the S to come down. It has to be more orderly, like this order is going to drop, okay? So let's see. 1 mole of gas going to 2 moles of gas, so no, that's increased. 1 liquid going to 3 gas, that's increased. 3 gas going to 2 gas, that one's coming down. 3 gas going to 2 gas, okay? This one is 1 solid going to 2 aqueous, so that's going up too. So only this guy, the third one. All right, let's go to the next question here. This next question here, it says, what is the pH of the solution prepared by mixing 40 mils of 0.1 of this acid here with 40 mils of 0.01 of this salt of the conjugate base. So you see how this is like the ion and then the H. This is the ion and the sodium. So this is the salt of the conjugate base. And it says assume the volume solutions are additive. So they just add together 40 and 40. And that's the total volume right there. And the Ka for the acid is 1.8 10 to the minus 5. Okay. So what's the pH of this? So can you tell this is a buffer? That's the acid, that's the conjugate base. So this is going to be our buffer. So to do the buffer, you need our equation pH equals to pKa plus log base over acid. So you just need the ratio of the base and acid, which they gave us. This is the acid, that's the base. So you should be able to tell how much base or acid that you got. Okay, so let's continue here. pH is what we're looking for. So pKa is minus log of Ka, so minus log 1.8, 10 to the minus 5, plus log of base or acid. So you can just take the, see how the volume is the same? So you can just take the molarity here to do the ratio. So the base is 0.010, and then the acid is 0.10. So it's 0.1, like this is like 1/10 of this number, right? So it's 0.1. So you gotta get that value put in, and you put it in your calculator. You end up getting 3.74 as your answer here. Okay, so that works. Now let's go to the next question. So this question here says, please type in the freezing point. So it says an aqueous solution has a normal boiling point of 104.6 degrees Celsius. What is the freezing point of this solution? So they gave you the boiling point. They want you to find the freezing point. So what you do here is you need to remember our equation is delta TB equals to IM KB, and delta TF equals to IM KF. So you can get your information for delta TB here because the base boiling point, right, the normal boiling point of plain water is going to be 100, and this is 104.6. That means the delta TB here is 4.6 Celsius. Agree? It's 4.6 right there. And then you need your I and M. Obviously, we don't know what it is, so I'm going to leave it as an IM right there. But we know our KB. KB is given to us. It says it's 0.51, and it's Celsius per molality, so that's good. So this is in Celsius. That's a molality. That works out great. Our units match. So what you do is you solve for IM, okay? And IM is going to be 4.6 divided by 0.51 here, which ends up being 9.02. Okay, now because this is the exact same solution, your IM can directly translate into this term in here. So then I can say delta TF equals to 9.02 times my KF, which is 1.86, which is also given in the question. Okay, so then it's going to be a big number here. It comes up to be like 16.78, well, bigger than this one. The freezing point depression is always going to be bigger than the boiling point elevation just because this is 0.51, this is 1.86. The impact for freezing is going to be bigger. So if the delta TF is 16.78 in Celsius, what is the actual freezing point? The original freezing point for water is 0. And if it goes down by 16.78, that means my freezing point is actually going to be negative 16.78 Celsius. So it says here, please type the freezing point with 1 decimal place in units of Celsius. So I'm just going to be typing like 16.8. And don't worry when you're typing in Celsius, if you don't form this, you just write Celsius, it's fine. The units don't carry any points. They actually put all the credit on the number itself. But you would probably have to type in the negative. If you put in positive, you would have gotten the wrong answer. You have to type negative 16.8 over here. Okay?
Can you tell me real quick how you got the 4.6 again? I'm sorry.
Sarah, what's that? How I got this number here?
No, the 4.6 for the delta.
Because we started at 100 degrees here, and then we went up to 104.6. So you have to remember the water's freezing point is 0, the water's boiling point is 100. So that's why this is negative 16.8, because it was based off 0 and went down 16.78. And that's why this is 4.6, because it started out at 100, but now it's 104.6. So my delta TB is 4.6. Okay?
Thank you.
You're welcome. All right. So let's continue with the next question. Lots of ground to cover today. So give the expression for KF for this guy. So you're finding KF. So remember KF, a formation for this complex ion. You have to remember the equation. What was our equation here? You take your individual ions, which is cobalt 2 plus, and then plus SCN negative, but there's 4 of them. And then you make cobalt SCN 4, 2 negative. And all of these are aqueous. So everybody goes in the equation. So my KF here is going to be products over reactants, okay? So it's CO, SCN 4, 2 negative. That's my top, divided by CO 2 plus, and then SCN negative to the power of 4. So it looks like, I think this one matches that, okay? So the key is to remember how to write the equations. A lot of people mix up the KSP and KF, so try not to mix those up, okay? All right, so let's keep going. We have question 8 here. It says there's a Ka of HCN here. It's given. That's good. They gave us a Ka. And it says, what is the pH of an aqueous solution of sodium cyanide? So basically, you need to be able just to do a base problem, because this sodium here is spectator ion, is neutral. Cn is basic because it came from a weak acid. Okay, so you're going to write an equation for Cn negative plus water. So everybody's aqueous except for this guy, so I'm going to write water is liquid. And then base is a proton acceptor, so you make HCN, and then you have hydroxide left over. Okay, so I'm going to go ahead and write the aqueous in here. Now, and then we build our ice table, and of course, because they give us the Ka here, I'm going to need a Kb, so let's go ahead and look for Kb here. The Kb is 1.0 times 10 to the minus 14 divided by 4.9 times 10 to the minus 10, because it's Kw over Ka, okay? So let's get the Kb value in. Let's see what we end up with the Kb. I got it's really 2.1, but I'm going to write an extra number just in case. I actually don't round at all when I do this math. I keep it all in my calculator. I do write a few steps out so you can see. So 2.04 10 to the minus 5, that's my Kb here. And then you want to go ahead and set out your ice table, okay? So again, we're going to use our shortcut. We always use our shortcut for acid, base, and buffer stuff, okay? We're going to do, so we need molarity. So 0.1 was the molarity of sodium cyanide. So 0.1 goes here, and then 0 and 0, okay? And then this will be minus x plus x plus x, and then we'll take this minus x, we're going to cross this little guy off, and it'll be x and x over here. So let's go ahead and put this into the Kb term, and then we'll solve for x, okay? So 2.04 times 10 to the minus 5 equals to x times x divided by 0.1 minus x. Cross off this little x here. X squared now, okay, it's 2.04 times 10 to the minus 5 times 0.1. And that gives me 2.04 times 10 to the minus 6. Okay, so you have to multiply these two terms to get this. And then you just take a square root of both sides to get your x, which is 1.43 times 10 to the minus 3. Now, so this is in molarity here, and this is molarity of hydroxide. So I can get POH. So POH is going to be minus log of this term here, 1.43 times 10 to the minus 3. That equals 2.85. So look at this here. Did they ask for pOH though? They asked for pH. So don't circle that, okay? You actually want to do pH equals to 14 minus 2.85, which is going to be 11.15. That answer right there. Okay, so hopefully everyone's good. And then you see how there's another answer here, 1.4, that matches this. So you have to be really careful and not. So a lot of times I actually think multiple choice is actually trickier because all the answers you get on the way shows up here. Okay, so sometimes maybe open-ended might be easier, it's less confusing. But over here, just remember the answer is 11.15. You have to get the pH. All right, let's go to the next question. This one here, it says, when titrating a weak base like ammonia with nitric acid, which is a strong acid, okay? Nitric acid is strong acid. You have to remember like sulfuric acid, hydrochloric acid, nitric acid, those are strong acids commonly used and seen in lab. So it's a weak base and a strong acid. So what does it say? So we just have to pick a true statement, like which one matches, right? So just by looking, I can see a weak base and a strong acid. I know the equivalence point pH will be slightly acidic, so it will be less than 7. So it's not going to equal to 7. It's not going to be greater than 7. It's actually going to be less than 7. Then you actually don't have more acid or base. You have equal amounts of acid and base. So that one's not true either. So let's look for one that says less than 7. So, and that one's not true because you don't use more base. pH will be less than 7. Okay? All right. So let's go for the next question here. We got to find K. So this question here is basically manipulating K. We have line 1 and line 2 and line 3. So line 1 and line 2 to get to line 3. Okay? So you just pick, okay, what is in line 1 that I can use to try to fit it into line 3? Well, I see the obvious thing is this guy, COH2, and there's none in line 2. So I want to fit this down exactly here, and I want to keep line 1 the same. So keep line 1 the same. And then let's take a look at line 2. What do I want to use? I can see that I can use this ammonia here, and again, it's exactly the right amount on the right side. Well, that's nice, and then that's also matching exactly. So I'm going to go ahead and keep these two the same and add them up. When you add them up, does the other stuff cancel off? So you get this. Oh, you have to cancel off the copper. Yes, those cancel off. The hydroxides as a product here, so that's good. So only thing you would do is you cancel the copper. So it all works. You just add up lines 1 and 2, you get lines 3. So line 1 plus line 2 gets line 3. That means the K for line 1 has to multiply by K of line 2 to get K of line 3. So what you would do is take these two numbers and multiply them together. Okay? Hopefully you guys remember how to do that, and then you'll be able to get the answer here. So take 1.6 10 to the minus 19 times 1.7 10 to the power 13. Multiply them together, you get 2.72 10 to the minus 6. So yeah, you're actually getting A here. Okay? All right, let's keep moving. So this question here is talking about catalysts and stuff. It says this W going to Z is uncatalyzed. The addition of a catalyst for the reaction of W going to Z will probably do something. Will it decrease A, B, and C? Decrease A, but B and C are constant, and then we have other choices. So let's see. If you put a catalyst in, a one-step catalyst, what will happen is you will lower the activation energy. So this will be your highest point now. Obviously A will drop. B will also drop because B is going to be up here now. but C stays the same because C is the difference between reactant and product. That one doesn't get affected, but because the hump is lower now, activation energy is lower, you do lower the top peak. So A is smaller and B is also smaller. Okay, so the answer will be decrease A and B, but C stays the same because you're not going to match this level of reactant and product is still staying the same. So let's look for an answer that matches that. That would be decrease A and B, but C is constant. Okay? Right, this guy here. Okay, so let's go to the next question. Over here, we're on number 12. Consider the following reaction and its equilibrium constant. So here's the reaction. Well, that's nice, it's all 1 to 1 to 1. K is given. A reaction mixture contains a certain amount of all these guys. Which of the statement is true? So when I gave you these concentrations here, these are going to be Q concentrations. So all you do is you find Q, and then you compare Q to K to see which way it will go. Okay, so let's take a look at Q here. Q is going to be SO3, so it's 0.12, NO 1.4. They're all 1, so I don't have to do any power to it. It's all power of 1. SO2 0.49, NO2 is 0.14. Oh, this is 0.14 also. Okay. And you get your answer to be 0.24. So Q is smaller than K because K is 0.33, Q is 0.24. So when it's smaller than K, that means you have too much stuff on the bottom. When you divide by a big number, the bottom, the answer gets smaller. So too much stuff on the bottom, which is reactants. If there's too much reactant, it will shift right towards the product side because we want to reduce the reactant and increase product. So I would say the answer would be B here, okay, because we have a shift right in the direction of products. Okay, so let's go to the next question. It says, which of the following here does Kp equals to Kc? So Kp equals to Kc when delta N equals to 0 and you don't count solids or liquids. Gotta remember that, okay? So let's pick one that matches that. This is one gas, don't count that one, going to two gas. Not the same because it's 2 minus 1. Delta N is not 0. So not this one. Let's keep going. 2 moles of gas, 1 mole of gas. So 3 moles of gas going to 2 moles of gas. Again, that's not 0. It's not equal. Delta N 0 means moles of product minus moles of reactant equals to 0. So the moles of products and reactants are the same. These two are wrong. None of the above have Kc, Kp. Well, we don't know yet. We've got to check these two first. Okay? So remember I said none of the above. It really means none of the rest of the answers. Okay? Because sometimes they jumble the position. And then C, that's solid. I don't count that. So 1 mole gas and 2 moles of gas. Again, that doesn't match. That doesn't work. And let's take a look at this. This one doesn't count as solid. So there's 4 moles of gas. That one doesn't count. 2 4 moles of gas. This one matches. It's 4 and 4. So 4 minus 4 would be 0. Okay, that would give me Kc and Kp have the same value. All right, let's go to the next question. This one here says, there's a sample of acid titrated with base. What is the pH after 12.9 ml of base is added? So Ka, a butanoic acid, is given. So this is a weak acid and this is a strong base. Okay? So they want you to find what's the pH after 12.9. So you can see that you have 24.2 mils of 0.150. This molarity is bigger. And if you want to get to equivalence point, it would be, you would have to have more than 12.9 mils of 0.146 molarity, just because it's 1-to-1 ratio there. And you can see here, if you were in a titration curve, right? Like, you know, you start adding your acid, add your base, and you just jump. So this is the equivalence point right here. You're probably somewhere like over here. So this here is the buffer region. Okay, a buffer region. So I'm going to use my pH-pKa equation, but we have to obviously find out what the base and acid ratio here. So let's go into the equation of what happens here. So butanoic acid, I'm just going to call it HA, plus hydroxide. So weak acid plus a strong base is going to be, sodium is just bacterial acid. I'm going to take this hydroxide. It's going to make water and butanoic ion. So I'm just going to put A minus there. Okay. And I need to find out the ratio of this guy to this guy, because that's my base and acid of my little buffer region. So we got to find the moles of that. So we're going to do moles before regular moles addition of OH, and we're going to do moles after addition of OH. Okay, so what I'm going to do is go ahead and calculate the moles of the acid and the moles of the base that we add, so we can kind of see where to start from. To get the moles of acid, you take the volume, divide by 1,000, and then you times 0.150. Okay, so 24.2 divided by 1,000, and then times 0.150 moles, 1 liter. That should give me moles of acid. So it's 3.63 times 10 to the minus 3 moles of acid. Okay, I got that moles part down. Then I gotta find out how much base I have. So I use 12.9 mils for base, so 12.9 mils, 1 liter, 1,000 mils, and then 0.146 moles per 1 liter. So that would be my moles of base there, okay? Let's see what I got here. It's 1.88. It's a long number. I'll just write it out loud. 1.8834 times 10 to the minus 3 moles. So I know my moles of hydroxide that's added. I know how much acid I started off with. I can go ahead and fill this table basically. So I initially, before I put any base in, I had 3.63 times 10 to the minus 3 moles of acid. That's just the acid part, okay. Running out of space there. And then I am going to add, this is 0, 0, so 0 and 0. And then we're going to add 1.88 10 to the minus 3, so 1.8834 10 to the minus 3 moles of hydroxide. Okay, so this guy will be used up to react with that. So the leftover is 3.63 10 to the minus 3 minus 1.88 10 to the minus 3. That will give me your answer here. Okay, so take 3.63 10 to the minus 3 minus 1.8834 10 to the minus 3. I get the answer here. And then for the A here, so this one ends up being 0. It will be addition from 0 adding 1.83 10 to the minus 3 to get this. So I'm going to go ahead and say this one is 1.8834 times 10 to the minus 3 moles of A minus. And then this one here is 3.63 minus 1.88. That comes up to be, it comes up to be 1.746. times 10 to the minus 3 moles of HA. So now I have my base and acid ratio here. Okay, then we put it in a pH-pK equation. So pH equals to pKa, which is given minus log 1.5 times 10 to the minus 5. That's my pKa. Plus log of base over acid. So the base is 1.8834 10 to the minus 3 divided by acid 1.7466 times 10 to the minus 3. Right there. Okay. And then you'll be able to get your pH there. It ends up being 4.86. Okay. So that would be our pH there. All right, let me know when you guys have questions. Otherwise, we are going to keep going. The class is going to run a little longer because we do have a lot of problems to go over, but feel free to come back and watch the video later if you don't have time now. So this is the next question. There is a rate of appearance of, this is my reaction here, rate of appearance of my product is 1.64 moles per minute. What is the rate of disappearance of this reactant at the same time? So you just have to remember this is like the first kinetics part that we learned way long time ago. That rate can be written using any reactant or any product. Okay, so obviously these are the two items that they chose in the question. I'm just going to write the rates for these two here. So rate here can be described as, if this is a product, is positive 1 over 2 delta CR2 SO4 3 over delta T. This little thing here has been given. It's 1.64 moles per minute right there. Okay. And the rate also equals, you can use a reactant. When it's a reactant, it's negative 1 over the coefficient, which is 3. And then we got to do delta change of C2H6O over delta T. And this is the rate of disappearance that they're looking for. This is 1.64 right here. So all you have to do is look for that guy. So then you take 1.64 divided by 2 equals to minus 1 over 3 of that. So to get my answer that I'm looking for, delta change of C2H6O2 over delta T, because it's a disappearance, it's going to be a negative sign in my calculations. It's going to be 1.64 divided by 2 times negative 3. Can you guys see that? And I will get my answer as negative 2.46. Okay, so you got to take 1.64 divided by 2 multiplied by negative 3 to get that. This answer right here. It's just algebra. And so our negative sign here symbolizes disappearance. So if they already asked for disappearance, they know it's going to be a negative sign. So the answer will be A over here. Okay. Let's keep going to the next question here. According to this voltaic cell, which species is being oxidized? So you just have to take a look at the picture. Well, you got to know anode is where electrons leave. So this is anode side. Where oxidation is, this is cathode side. It makes it easy. So who's being oxidized? This guy is being oxidized because it's CD going to CD2 plus, and then cathode is reducing, so it's Cu2 plus going to Cu. So you'll be able to tell, like, you know, which one's being oxidized pretty easily. If they ask which one's being reduced, it's obviously going to be copper 2 plus here. Okay. All right. We are going to keep going to the next question. There we go. now we have to calculate delta G of this reaction. And they gave you the formation values of all these guys here. Now the one that they didn't give you is N2, because N2 is 0. Okay? So delta G of my reaction is going to be total of my products minus total of my reactants. So my products is 7 times 0, because N2 is 0, plus 12 times negative 237.1. That's all my products. And then I have to do minus my reactants, which is 4 times negative 73.5 plus 5 times 149.3. Okay, you put this on the calculator. Be really careful if you're doing it straight that these signs change because it's negative over here. And you end up getting, let's see what I got. Negative 3297.7 kilojoules. So it's negative, so it will be this guy here, 3000 plus. Okay? All right, let's go to the next question. So this one is something we just covered, so it should be pretty easy to remember. Let's take a look at the mechanism problem after this here. So this mechanism problem here, possible mechanism, this is from Kinetics chapter. Remember, you have to find rate law. And the rate law is limited to the slowest step. So we're going to take a look at this step here. And you got to make sure there's no intermediates, which obviously there's going to be an intermediate here. Do you guys see an intermediate? You put NO in, you put BR2 in, you make NOBR. You use NOBR in step 2, and then you put another NO in, you make NOBR. So this one here is my intermediate. Okay? So if I know that's my intermediate and my slow step is step 2, rate is actually going to be K step 2, NOBR 2, and NO. Because you write it for the reactants. Then you say, this is my sad phase. And then we have to like look at step 1 and replace it, okay? So when we take a look at step 1, remember rate forward equals rate reverse. So I'm gonna write rate forward, which is K1 NO times BR2. And then K reverse is K minus 1 NOBR2. Yay, that's the term we want to replace. So let's find out what NOBR2 is. NOBR2 is going to be K1 over K minus 1 NO times BR2. And then we take this big term, plug it over here. Okay, so let's rewrite it. Rate now is K2 and then K1 over K minus 1 NO BR2. That's the substitution we do, and then another NO. Okay, so you can see it's K2, K1 over K minus 1, 2 NO, so NO squared, and then BR2. So it looks like this one matches. Okay, so that's mechanism here. So if you can't remember all these things, you gotta go back and do some review. But this is how we would do a mechanism problem here. All right, let's go to the next question here. We are number 19. Which indication of relative acid strength is incorrect? So they want to find which one is wrong. So is HClO2 stronger than HClO? Yes, that's true, because you are looking at how many oxygens in this case. Okay, so you have to remember how to judge different acids. There's oxyacids and binary acid. For oxyacid, if it's like this case here, you're looking, the more oxygen you have, the stronger. And this one here is a binary acid. Binary acid going down is getting stronger. So HCl is bottom of HF. F is on the top of the table. Cl is on the bottom. So yes, HCl is stronger. So this is correct. And then now you have both of them are 3 O's, but one's S and one's nitrogen. The more electronegative guy is going to be stronger. Okay, so who's more electronegative? Nitrogen or sulfur over here? So in this case, a nitric acid is actually going to be stronger. Okay, so this one here is incorrect. Incorrect. And then this one here, you got 4 oxygens and 3 oxygens, so that's still correct. Okay, so that's what we're going to be doing here. Let's go to the next question. The next question here, we have what is the ratio of this guy to this guy? So this is my base and this is my acid. So what's the ratio of base to acid to make a buffer for a pH of 4.04 and they gave you the Ka? So all you do is pH equals the pKa plus log base over acid again. So when you're looking for this, you don't even have to break that apart. Just look for that guy. Okay, so all right, so pH here is 4.04, and then 4.04. pKa is minus log 1.8 times 10 to the minus 5. And then plus log base over acid. Okay, this ends up being 4.74 here. 4.04 plus log of base to acid. So that would give me negative 0.70, because it's 4.04 minus 4.74. So negative 0.70 equals to log base over acid. And then I'm going to take 10 to the power here. So 10 to the power of 0.7, negative 0.7. Let me write it nicely. And you'll get your answer. In this case here, that equals to 0.197. So it's going to be like 0.2 to 1. 0.2 to base to acid. So 0.2 is the answer right there. So I would pick C. Okay? All right. Let's go to the next question here. We just did this recently. This is liquid going to gas. So my delta H and my delta S are both positive. And if you plug in your delta G equals to H minus T delta S, you'll find that at low temp, okay, you find, remember like low temp is 0.1 and the high temp is 10. You'll find that low temp is going to be non-spontaneous. And then high temp is going to be spontaneous. So you replace 10 here and low temp is 0.1. Plug it into the equation. So you just have to find an answer that says low temp non-spontaneous, high temp is spontaneous. So I think it's at low temp, the reaction is non-spontaneous. That's good, delta G positive. And at high temp, the reaction is spontaneous. Yeah, it's this one. It's D. Okay? All All right, so that one we just covered, so I'm just gonna go over that. And then this one we just did also for our test, so let's just do this one quickly because it's acidic balancing, and you'll have to be able to tell this is being reduced, this here is being oxidized, okay? Nickel is going down, so I'm gonna go ahead and do my oxidation line and my reduction line. Oxidation is NH4 goes to NO3, and then my reduction line is Ni2 plus going to Ni solid. Okay, N and N are balanced, so that's good. And then if I see oxygen, I put water on the other side, so 3 waters. If I see hydrogen, I put protons on the other side, so 6 plus 4, 10. And then we want to balance charges. So this is positive 1. This is 10 positive minus 1, so it's positive 9. To balance it, I have to put 8 electrons in. Okay? So now both sides are the same. Let's go to this question here. Nickel and nickel are balanced, so all I do is put in 2 electrons here. So then we have to combine them, and I'm going to take this and times 4. So it'll be 4 nickel, 2 plus 8 electrons going to 4 nickel solid. And then this one keep as is. So they ask you, what are the coefficients in front of Ni and H? Well, Ni is going to be 4, right? And H plus is going to be 10 right there. So it would be that guy. Okay? All right, so let's keep moving. Now I am doing this really fast because at this point I expect you to already have known how to balance. And if you still don't remember how to balance, you got to go back to the lecture part while we were doing this really, really slowly so you can see step by step. Look at your notes, okay? All right, let's go to the next question here. Number 23, the lowest freezing point. So non-volatile solids, you should assume ideal Van Hoff factors. Okay, perfect. Ideal Van Hoff factors, that's nice. So that means they split according to how many ions you see. So you see the molality is all the same. So the lowest freezing point will be the lowest, biggest delta TF, which is IM/KF. If you notice, everybody's KF is the same because they're all aqueous. So it's 1.86. Everybody's molality is the same because it's 0.075. So all I have to do is look at the I. The biggest I is going to give me the lowest freezing point. So what's the I for this guy? 3 ions and 1. The I here is 4. This is 2. This one's 2. This one's 2. This one's 2. So my answer would be A here. Now, if they ask you what's the highest freezing point, the answer would be like, well, one of these guys, because they're all the same. Okay? So hopefully you guys remember this from the beginning chapter. All right. So it says here, consider a reaction. The equilibrium will be displaced to the right. So it will shift right for the next question here if we do something. So the options are like remove CCl4, remove chlorine, lower pressure, temperature raise. So let's take a look over here. This is exothermic, so my heat is going to be on the product side. And then if you want to shift it to the right, the first option it says is remove CCl4. Yes, remove CCl4, it will shift right, so that's good. And then chlorine gas is removed. It's not going to be the answer because if you remove chlorine gas, it will shift to the left. And then the pressure is lowered. If the pressure is lowered, both sides have the same amount of moles of gas, so it's not going to make a difference. And then temperature is raised. If you raise the temperature, your increasing product, it will actually shift to the left. So the only answer that would make sense is actually A here. Okay? All right, let's go to number 25. Number 25 here is something we just recently did, so should still be fresh in our memory. It says here, how long, so how many hours must you pass a current of 50 amps through an electrolytic cell, copper 2 plus, so it's 2 moles of electrons to 1 mole of copper, to produce 5.5 moles of copper. So I'm going to go ahead and write it down. So 50.0 coulombs per 1 second from the amps. And I know I have 1 mole of Cu to 2 moles of electron. I'm just writing out what I see here. So that's what they gave me, and I started off with 5.50 moles of copper. And I want to get all the way to hours. So moles of copper, moles of electron. How do I tie moles of electron to coulombs? That'll be Faraday's constant 96485. 1 mole of electron. So I'll use that. So I'll go copper, moles of electron to coulomb, coulomb per second, and then seconds to hours and minutes. That's what I'm going to do. So 5.5 moles. I don't even need the molar mass here, but if you needed to, you can look it on a periodic table as well. But we don't need it here because they gave us moles. If they gave you grams, then you would have to convert the grams to moles first. So 1 mole Cu, 2 moles electron, and then 96485 coulombs, 1 mole of electron, 50 coulomb 1 second. 1 minute has 60 seconds. 1 hour has 60 minutes. So put it all in your calculator, you will get your answer. And I am getting 5.9 here. Okay? All right, so let's keep going. The next question here. What is the molar solubility of silver chloride in water? So molar solubility is S, and they gave us the KSP. Oh, that's nice. So AgCl's KSP formula is AgCl solid going to Ag plus Cl negative. So it's actually like KSP is Ag plus times Cl negative. Okay, so we have that here. Now we want to go ahead and set an ice table, ICE. And because it's in water, this is 0 and 0. So it's going to plus S. That's S and S right there. KSP equals to S times S, which is S squared. So we're looking for S and we have KSP. So 1.8 times 10 to the minus 10 is S squared. S would be square root of that answer. You get 1.3 times 10 to the minus 5. So that guy would be my answer. Okay, so this one's a pretty simple because it's in water. If it wasn't in water, you just put whatever ion that's in there, you put the molarity in. Okay, all right, let's take a look at the next question here. The next question here is, what is the pH of pyridine? This is a weak base because Kb is given. Pyridine is a weak base, and it's so nice they told you that. I assume Kb is very small compared to initial, so go ahead and use your shortcut here basically. So all you gotta do is say pyridine is my base. So again, you don't have to write the whole formula, you can just say base plus water is gonna give you H base because you add a proton to it, plus hydroxide. And then we're looking for pH, okay? So when you get your X, you get the POH first, and then you take 14 minus that to get pH. So I am going to put in my molarity. Actually, let's, Kb is given, okay. Which is 0.600 minus X plus X plus X. 0.6 minus X, I'm going to cross this one off, X and X, okay? And that is going to set to equal to Kb value, so I'm going to work it on this side over here. Kb is 1.9 times 10 to the minus 9 equals to X times X over 0.6 minus x. And I'm going to cross out this little x here. So x squared is 1.9 10 to the minus 9 times 0.6. Okay, and that should give me an answer of 1.14 times 10 to the minus 9. It's really longer than that. I just write some number down, but I don't round it in my calculator. And then we take a square root of that. You get x value, which is 3.376 times 10 to the minus 5. So that would be my molarity of hydroxide right there. So I can get POH. So POH is minus log of this number, x here. I'm running out of space, so I just write x, okay? And you get POH as 4.47. So pH would be 14 minus 4.47, which you're going to get 9.53 here. Okay? So that's how we would do this question, number 27. So let's keep going. Let's do number 28. Which of the following compound will have the lowest molar solubility in pure water? So lowest molar solubility. So smallest S. Okay. So you want to compare S. So you technically would have had to calculate all the S from the KSP. But the good thing is all these guys have 2 ions. If they all have 2 ions, you don't have to do the math like you get the S from KSP, because that takes some time. So what you want to do is say the lowest molar solubility would relate to the KSP that's the smallest. So you just look for the smallest KSP in this case. Which the smallest one will be this guy. Okay. Now remember, we just did a problem here where we can find S from KSP. We just did one like right here. Number 26 here. So that's what you would have to do if you're all mixed up. You would have to do the S for every single one and then compare. But since this one all had the same 2 ions, all the same formula, you can simply pick the smallest KSP here. Okay? Okay, let's do number 29. So 29 here is they want you to put the pH in 2 decimal places, so it's finding pH. So here's a buffer. 1.27 liters of buffer, total buffer. This is the molarity of the acid, molarity of the base. Well, that's nice, it's 1 to 1. So this is a buffer where it's like pH equals to pKa. Okay? And then it says, calculate the pH of solution after you add 0.06 moles of solid NaOH. So you're adding NaOH into your buffer, and they gave you the Ka. So what you will do here is you'll have to use, you have to find out, the base, addition of base here will self-sacrifice the acid. So HF is going to react with the incoming hydroxide to neutralize so the pH won't change a lot because this guy self-sacrifices. And then you'll make water and F negative. So you have to find a new ratio on F and HF basically. Right now it's 1 to 1. After you add the OH, it's not going to be 1 to 1. It'll change a little bit. Okay, so let's go ahead and put the table in here. So you have to put the moles before addition of OH and then addition of OH, and then moles after addition. Okay, we're talking moles here because I don't have to deal with the liters, so I'm just going to go ahead and get the moles. So get the moles is 1.27 liters times 0.232. That's the original moles of acid. So just take 1.27 times 0.232. Circle this. You can get moles of original acid and base, right? So I'm going to go write that number is 0.29464 moles HF. And since it's the same molarity for NaF, it's the same 0.29464 moles of NaF. And remember, Na is just spectator iron, it doesn't really matter. We're really talking about F here. Okay, so the before addition, I have 0.29464 of this guy, 0.29464 of this guy. That's before. Okay, my addition is 0.060 moles of this guy. So this answer here will be 0.29464 minus 0.060. And this answer here would be 0.29464 plus 0.060. Okay, that's my new ratio there. So this answer, let me make sure this is 0.20603,464. And then this one is plus, so 0.35464. Those are my new ratios. And I'm just going to plug it into my buffer equation where pH equals to pKa, which is minus log 3.5 times 10 to the minus 4, plus log of base, this is my base, 0.35464 over 0.23464 acid. And then you should be able to get the answer. So that would be, it says 3.64. Okay, so this was from test 2, so hopefully we remember how to do this. I also worked this in class before and on our review as well. So here's another review. Okay, all right. So let's go to question number 30. For question number 30 here, we are going to do titration. This is my strong acid. This is a strong base. So how do I remember strong base? It's because it's group 1 and group 2 hydroxides. Okay, this is group 2 hydroxide, strong. So this is strong and strong. So here's the trick. When this one has 2 hydroxide, the mole to mole ratio is not 1:1 anymore because this only has 1 mole H and this one has 2. So you actually need double the amount of acid. So if you were to write an equation, you would say HNO3 plus CaOH2. You would literally need a 2 here so you can make 2 waters. And then CaNO3, 2. Okay, so you got to remember you need double the amount of acid here. So the molarity is the same. You have 80 mils, so this one you'll need double the amount, which would mean you need 160. Okay, so don't pick 80 because 80 is right there staring at you. You got to remember this one has double the amount of hydroxides. So the answer would be 160 mils, which would be this guy. Okay, all right, let's go to number 31. Now, your test only has 30 questions, but 5 bonus. And on this review here, we have 40. So, like, you can totally do it. Like, there you have plenty of time because they gave you, like, I think, like, almost 2 hours to do it. So, yeah. And I'm here talking and going through stuff. And we're doing a lot more problems, too. So, anyway, calculate the cell potentials that take place with this reaction here. So this is a concentration cell. So we just did this one recently where you'll have to remember, in this case here, my oxidation is Fe going to Fe3 plus 3 electron. And this one here is 0.0011 molarity. And then the reduction is on this end, which is Fe3 plus, this is a 2.331, plus 3 electron going down to Fe solid. So this is solid. Okay, so I can see where my Q is here. This is products, this is reactants. So E cell equals to E naught cell plus log, not log, not plus, it's minus. This equation is given, don't forget. Don't. E cell minus 0.0592 over N, which is 3, log of Q. Now Q here is what? Products or reactants, okay? So 0.0011 over 2.33. And the E cell here, because it's concentration cell, this is going to be 0. Because one's positive, one is negative, they cancel each other out. So your answer is going to be an itty bitty answer, but it's going to be positive here, 0.066. There, matches B. Okay? So that's number 31. Let's go to number 32 here. We have 2 equations. It says, which of the following species is the strongest reducing agent? So there's only 2 to pick from. The strongest reducing agent is the one that loves to oxidize. So who's going to oxidize in this picture here? I would say this guy, because you flip the negative one. So Mn is going to be the one that's oxidized. So it's the strongest reducing agent because it loves to be oxidized the most. I would say Mn is my answer here. Okay, if they ask you strongest oxidizing agent, the answer will be the opposite. You would pick this guy. Because strongest oxidizing agent loves to be reduced, so it'll be Br2 liquid. Okay? All right, let's do the next question. Henry's law. So this one is a long time ago, but it's a very simple question. So it says here, Henry's law's constant for helium gas is given. So they gave you the constant. Since the partial pressure is 0.65, what is the concentration of helium in water? So the formula was solution of my gas equals to the Henry's constant for my gas times pressure of my gas. So we are looking for solution concentration. And KH is 3.70 times 10 to the minus 4 molarity per ATM. And the pressure is 0.650 ATM. Well, that's easy. All you do is look for the molarity. Multiply those 2 terms together. So you get 2.41 times 10 to the minus 4 molarity. Okay? So that's how you do Henry's law. Gotta remember this equation. All right, let's take a look at number 34. Says here, the KW is 5.5 10 to the minus 14. This is 50 degrees. An acidic solution, remember acidic solution, you'll have more H than OH. And this is probably the middle point here. I'll show you how we got that. So H times OH equals to 5.5 times 10 to the minus 14. And if you assume it's pure water, you will solve it for x here. So it would be x times x. So square root of 5.5 10 to the minus 14 would give you this term here. So if we solve this as x here, that's how you get 2.3. But obviously this one's given to you, so you didn't have to calculate this. But I want to show you just in case you needed to. We would do square root of 5.5 10 to the minus 14. X would be, I'll just do that. Which in this case is 2.3 times 10 to the minus 7. And then so your answer would be hydrogen ion will be bigger than 2.3 10 to the minus 7. And then hydroxide would be less, because it's acidic. So this one matches the last one. Okay? All right. Let's take a look at number 35. It says here, which species will oxidize H2? So where's H2? H2 is right here. You want to oxidize this. Has to be the line above it that's being reduced. So my answer is I2 solid has to be the species that does it. because I2 is going to be reduced for H2 to be oxidized. So I gotta pick D. Okay, so that's number 35. Let's go to number 36 here. What is the conjugate base of H2PO4? Negative. So this must have been acting as an acid. An acid donates a proton, so you will lose a proton here. So you pick the one that drops off a proton. Okay, so remember, if you're looking for the conjugate base, it acted as an acid. So a lot of times they think it's acting as a base, and then you get the wrong answer, which the wrong answer would have been like that one right there. People might pick that. But you want to make sure you read the question carefully. All right, let's take a look at number 37. Carbon 14 has a half-life of 5720, and this is the first order reaction. If a piece of wood has converted 75% of the carbon, and how old is it? So we've actually done this question in class before. If you look at our notes, we did the exact same question. But this question here is saying you converted 25%, so how much is left over? You are at 25% that's left over. Okay, so you could have used this equation. Okay, and you can calculate it, but yeah, because they have a half-life, you get the K, you put 100, this 25, but I wanted to show you a shortcut here. 100% goes to 50% goes to 25%. If you're exactly at the half-lives here, this is one half-life, this is a second half-life. All you do in answer is literally take the half-life times 2. It only works if you fall exactly at 50 or 25 or 12 and a half. You cannot do any other numbers. Any other numbers that's not pretty, you have to use this formula. Because it's a curve, it's not a straight line. So my answer would actually be this guy. And if you use this formula, you would have gotten that answer. Okay? So I just wanted to remind you guys about this. And we've done this in notes too, so look back on your old notes and you'll see it as well. All right, let's take a look at number 38 here. Number 38, we have a question for aqueous solution that's 10% by mass. So when it says 10% by mass, every time I have 10 grams of ammonium chloride, I actually have 100 grams of solution. And they want you to find a molarity. Okay, so to find a molarity, you turn this into moles, you turn this into liters. And then you put them together for molarity, okay? So how do you turn this into moles? Well, you have the molar mass, we can do that. How do you turn from grams to liter? Well, you have the density. So that's what we will do, okay? So let's go ahead and do the moles first. Moles is grams of ammonium chloride. 1 mole is 53.5 grams. So we get moles of 0.187 moles. And then let's do the grams to liters. So 100 grams. This is exactly 100. So, and then density 1.0286 grams to 1 mil of the solution. And then 1 liter is 1,000 mils. So you get your liter of solution is 0.0972 liters. Okay, so you put this mole divided by this liter. You can get your molarity of 1.92 molarity, which would be that guy right there. Okay? All right, let's go to the next questions. We only have 40, so we're almost done. So thanks for staying for so long. We're almost done. And it will be recorded so you can go back and watch it later when you have questions. So let's take a look at this rate law. So to do the rate law, remember, 2 of them have to be sleeping, 1 of them is moving. So I can see that this is moving, that's constant, and that's constant, and this is moving. So this is times 2, this is times 2. So my BrO3 is first order. Okay, so if you don't remember how we do this, you might have to go back and look at our notes, okay? Now, then I want to pick another 2 lines. Which 2 lines? Actually, I can pick these 2. This one doesn't move, this one times 1, this one doesn't move. So this is times 1.5, and this was times 1.5. And see how this is constant? So that's good. So again, that matches to the power of 1 to the power of 1. So that's first order also. So BR is first order. Let's take a look at the last one. So we need to do H. So I'm going to do 1 and 4 because that's constant. That one's constant. And this one's going up by 2.5. And then this one's going up by 6.25. So 2.5 squared is 6.25. So that's second order right there. So H plus is second order. So I would just be able to pick the one that matches, and this one's second order. So actually, yeah, this one here, BrO3. Oh yeah, that one's not second order. This one's -2. It's this one right here. Yeah, I forgot to see the -2 right there. So you want to be the 2, 1, 1 right there. Okay? All right, so let's go to the last question here. We actually just did something like this for our class recently for our last test. So it says here, look at this reduction potential and then understand the conditions. We have to see who's stronger and who's weaker. So based on looking at this picture here, I have 2 options to oxidize and I have 2 options to reduce. So which one am I going to pick? Well, I'm going to oxidize cadmium because I know how to flip this line, and I'm going to reduce F2. Okay, so that means cadmium is a stronger reducing agent than F negative. So CD2 plus, stronger reducing. Do we have a CD2 plus here? No, this is even stronger. Oh, so actually they're doing, let's see, I better just read each line here and see which ones make sense. Oh, here it is. Here's the CD stronger reducing agent. Okay. And then F2 would be the stronger oxidizing agent. And so it's this one here. So it would be this guy, because I can see that I know I have to reduce F2 and oxidize CD for it to be spontaneous. So that means this is the strongest reducing agent in this list, and this is the strongest oxidizing agent in this list. So F2 is stronger than CD2 plus oxidizing agent, and cadmium is a stronger reducing agent compared to F negative, because you're comparing these two like that.